Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Eliza Barry from Business Review, and I will be your host for today. It is our pleasure to have Nidek Cato Engineering and Leroy Soma with us today, who will be presenting today's webinar titled Properly Sizing Your Generator. Today's guest speaker is Jacob Jewison, Electrical Engineer at Nidek Cato Engineering and Leroy Soma. I'd like to welcome you to our platform on 24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate some time at the end of the session to address any thoughts or questions that you may have. Please use the yellow help widget if you require any assistance, and you can move, resize and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Jacob.
Thank you, Eliza. So today we're going to be talking about mechanical considerations such as enclosure, altitude, environment, electrical considerations such as kW, power factor, operating temperature, non-ideal loading, transient performance. We'll also be talking about some agencies and how that affects the sizing and the characteristics that are required of a generator. So power generation can be required in a variety of locations, and each installation is going to drive a different requirement for the generator, some of which are going to drastically affect the sizing of the machine for the same kVA load. Environments that we see can range from sub-zero to 60 degrees C ambient. I've seen as low as minus 40 degrees Celsius required for a generator to be able to operate. And we'll also see generators below sea level and on mountaintops. These will have harsh conditions with a lot of sand and debris, and that will have a heavy impact on how we need to enclose and protect the generator. And approval agencies and customer specifications will often have their own requirements that will need to be considered as well for the enclosure type. The most common enclosure types that we're going to see are going to be an open drip proof, which is shortened down to ODP, a weather protected machine, also known as a WP2, totally enclosed water to air cooled, or a TWAC, also called a CACW, which stands for closed air, closed water. And we'll also see a totally enclosed air to air cooled TAC, or also CACA, which is closed air, closed air. The other one that we'll talk about a little bit that we don't have listed on here is totally enclosed fan cooled, which is TEFC. And those are not quite as common, especially at the sizes that we deal with here at Cato. So ODP is going to be kind of the standard option. When you hear me talk about oversizing for an enclosure, this is what I'm referring to when I say oversizing, meaning how much bigger it has to be than the standard ODP. So when this is cooled directly by ambient air being pulled through the generator by fans that are mounted on the shaft. And you can see on the picture to the right there are some vents along the top. We have a drip cover over top of that to make sure water doesn't get in that's coming straight down. We have guards and shrouds to maintain an IP23 rating. That has to do with water dripping straight down and also keeping more or less your fingers out of there so people can be safe to be around the unit. We can also filter the inlets if there's a little bit of debris in the air. This can cause it will cause a slight derate in the machine It might not be significant enough to oversize the machine depending on where it falls in our standard sizes. But it does happen quite often where a filtered machine will have to be a stack length bigger than a non-filtered machine. So again, this is our standard configuration, and it's going to typically give the smallest physical package when we talk about our core's diameter and our stack length for a given kVA output. This is very common in engine rooms and other controlled environments. You will not see an ODP just sitting out in the open. WP2 is our weather protected type 2, and this is cooled by the ambient air being drawn in through the air duct that you see on the top right side of the picture. And again, we have the shrouds and the covers to maintain that IP23 rating. Part of the requirement of the WP2 is that the inlet air has to make at least 3 90-degree changes in direction, and this is to help slow down the air. And you can see at the directly below the air intake, there's the little section that comes down a little bit further than the rest, and that's for particles and moisture to collect. So as it comes in and travels down, those particles in the air will fall out of the air as the air gets kicked back around up into the machine. The air velocity is limited to 600 feet per minute, and the outlet air is ducted. So these WP2 machines will be about 5% larger than an ODP. Again, that's not always going to increase your stack length, but it does happen quite often. I would say typically it will increase, but there are a few cases where we can build the same kVA in a machine for ODP and WP2. So, and you'll see this a lot on land-based gas and steam turbine applications. Our TWAC is our totally enclosed water to air cooled. So we have air inside the machine with an internal fan moving it around, and that air is sealed in. It's never going to escape ideally. And then we have water ducted in through the top, flowing through, so that circulating air is pushed across the ducting that we have water flowing through, and that heat from the cooling air transfers into the water and then is pumped out of the machine. The cooling water that circulates through is typically less than 32 degrees C. We can get it down to the same core size as an ODP unless the cooling water exceeds 25 to 32, depending on some other factors, including sizing of the machine and whether it's single tube or double tube. Single tube is used more on land applications, and it can be copper, nickel, or stainless steel. Double tube means one tube inside of the other, so if the first tube leaks, the second tube can contain that water and make sure that that water doesn't get onto the electrical components. And these are copper nickel tubes only. Our totally enclosed air-to-air cooled machine is very similar to the TWAC machine, where we have circulating air inside of the generator that doesn't ever escape, but we have air ducts going through with outside air, and that heat is transferred from the inside cooling air to the outside cooling air on those ducts. These will typically be about 30% larger than ODP, and this meets our IP54 and IP56 ratings. And this is usually used when water is not available for a TWAC. So here we have a demonstration of, or a picture of how the TWAC will work. So we have air coming in on the left-hand side with the green arrows, going up to our air ducts sitting on top of the generator and flowing straight through by those, by the lighter blue colored arrows going straight through. So the outside air is never touching the core, the coils, anything like that, and then going out. And then we have the circulating air shown by the dark blue arrows coming in from the end, being blown by the internal fan through the shaft into the rotor. And then that hot air, as it crosses the rotor, which is producing heat, is pushed up through the vents in the stator and then goes back up into the cooler to be cooled down and have that heat transfer into our cooling air. Totally enclosed fan cooled, we have an internal air that forces air over the core and the windings to help circulate it and not let that heat sit in one location. But the heat is only radiated through the enclosure, and you can see we have fins on the enclosure to help that heat radiate out. There's an external fan mounted on the right-hand side in the picture here that is blowing in and blowing across those fans to help move that heat away as it radiates out to help cool. The totally enclosed fan cool is going to be about twice the size of an ODP due to the additional losses that we only see from the radiant cooling opposed to having air moving through. Again, these will need an IP54 to IP56 rating. And you'll see these in offshore petroleum applications where we're exposed to corrosive atmosphere. So altitude can play a big effect on the generator sizing. This is because as you get higher in altitude, your air gets thinner and means that you have less mass in the air to transfer heat effectively. So a generator that's intended for a high altitude location may need to be oversized to handle this lack of cooling, or we may need to have a larger fan to help compensate for it. One of the things that typically helps when you have a high altitude is there's typically a lower ambient temperature, but we still often have to rate the machine for 40 degrees Celsius, so that can help sometimes, but it doesn't always. So here we have a chart to show how much we have to derate by the altitude. Typically we rate our generators for up to 1,000 degrees. And you can see at 40 degrees C there's no derate there. Also, this derate is affected by the ambient temperature because as it gets warmer at a given altitude, the air is also less dense and also less capable of transferring heat. So also because the overall heat of the generator when it's hotter outside, there's less of a ratio, so we're not as hot compared to the ambient temperature. So we get a little bit less heat transfer through that as well. So again, we see here a higher than normal ambient, greater than 40 degrees C will have an impact on the sizing for all enclosures. And cold weather applications down to minus 30 degrees C and below will require special consideration for lubrication and materials. So that's going to typically cost a little bit more. It's not going to require an increase in size of the generator, but it will have specialty materials. All right, so we've talked about environmental factors and enclosure types. I believe we have our first survey question, Eliza, if you would read that off for them.
Okay, thank you so much. Okay, so it is now time for the first polling question of today. And the question today is, In order to understand more about our audience prior to the Q&A session, what department below best describes your current role? And the options that we have are procurement or purchasing, maintenance, facilities management, quality, sales, project management, other, or engineering. I'm going to give everybody a moment to make their votes now and select the option that is most applicable to them. Just a reminder to the audience, in order to ask any questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. Okay, so it looks like everybody's made their votes. Let's reveal the answers. Ooh. Okay, so looks like the majority is from sales and engineering. Okay, thank you everybody for voting. I'll pass it back to you now, Jacob. Thank you.
All right, thank you, Eliza. So now we're going to move on to electrical considerations. And these will also cause a size increase, but I will say that typically if we have a mechanical consideration such as the enclosure type or like an altitude, and we have an electrical, those won't both cause an increase. So kind of the increase that we do for the enclosure will also cover the increase that we are required for the electrical. That's typically the case, not always. So our basic electrical parameters for affecting size are going to be our kW or kVA and power factor, our frequency and RPM, our temperature rise, any non-ideal loading conditions, and any transient performance requirements. So still remember to keep the mechanical considerations in mind. So here we have our power triangle. Our active or real power is measured in watts, and this is what produces a tangible result. It's also known as, such as heat or light. It's also known as our I squared R, and this is also what puts torque on the motor. So this is typically what a motor company that's building combo units is curious about. Our reactive power is power that surges back and forth between the source and the load. It's what produces alternating magnetic fields and devices, such as transformers, induction motors. You'll also see it in capacitive loads. This is called our I squared of X. And so this is just current that's surging back and forth between the motor and the load. It's not putting any torque on the motor, but the generator has to be able to handle it. Our apparent power is going to be the vector sum of those two, and so this will be the total current that we have to handle. It's not purely additive. You can see the triangle. It's not all in phase with one another. So the best way that I like to describe apparent power is if a maintenance technician went up with a voltmeter and measured the voltage, wrote it down, measured the current, wrote it down, and multiplied the two, he would get the apparent power. He's not taking into consideration that the current and the voltage aren't perfectly in phase depending on how much reactive power we have. So our power factor is the cosine of the angle between our active power and our apparent power. Also, just that's a fancy way of putting it's the ratio between our active power and apparent power. So it describes how much of the power being produced by the generator is going towards actual work and how much of it is putting actual torque on the motor. So this is determined purely by the load. A lot of people think that because a generator is rated at 0.8 power factor means that it will constantly produce 0.8 power factor. And that's simply not true. This is purely determined by the load that you connect and how much of that load is inductive and how much of it is resistive. So you'll typically see a generator rated at 0.8 power factor, meaning we can handle rated kVA down to 0.8 power factor. And 1.0 is called the unity power factor, meaning that we have a purely resistive load and no reactive component. So for a given kW, if we have a lower power factor, we'll have a larger angle and we'll need a larger generator to provide that extra reactive power. Another way to think of this is when you drink a beer, you have the froth that hits your mouth first and delays the beer. The reactive power is similar to that delay, setting up the magnetic fields. The beer that flows into your mouth and quenches your thirst is like the active power. It's what you're actually getting out of your beer. The total amount of the beer and the froth in the glass represents the apparent power, which is the sum of the active and the reactive. So the way that I like to think of this, if we have a beer that we know is going to have a lot more foam on the top, we're going to need a bigger glass or more apparent power to handle both that reactive power and still get the active power that we desire. So here we have a reactive capability curve. And you can see for the inductive load where most generators operate, once we get below that 0.8 power factor where this particular unit would be rated at, we become limited by the rotor heating. This is because as you become more inductive in your load, you have more flux traveling back into the rotor against your field, which drives a higher rotor current. So this is going to increase our rotor heating. So we need to dial back the load that we output to maintain that rotor heating. When we get above 0.8 power factor, we get to where we are limited by the stator heating, and that's because we have our stator rated for a given kVA because we have to handle that current. And this typically goes down into a capacitive load, still limited there, and then it tails off. And that is because as you become more capacitive, you have that stator flux pushing with the rotor, and it becomes very unstable because you're kind of driving with the stator and your control system becomes more limited. We also have as we become very capacitive, we become limited by control stability. This was more of a problem with older analog control systems. Newer digital ones, this typically isn't a concern. Here we have another way of looking at that. Here we're just on the lagging or the top half of the last slide. You can see our kVA is at 100% down to 0.8 power factor. So we have 100% of our kVA, and then it becomes again limited as we go down in our power factor, becomes limited by that rotor heating, and then our kW is just the power factor times that kVA. So from 80 to 100%, it is just 80, 90, 100% of that kVA. And then as we go down, that kVA is also dropping. So our kVA, or our kW, will also drop a little bit with it. So frequency and RPM play a big factor on sizing of a generator. If we spin the generator faster, it's going to produce more power. So a 60 hertz will produce roughly the ratio of 60 over 50, more power than a 50 hertz machine of the exact same design. So the RPM of the prime mover and the frequency output drives the number of rotor poles that we need. This also affects the physical size of the machine. The formula for that is the frequency equals the RPMs times the number of poles divided by 120. It's often asked where that 120 comes from. It's because frequency is in cycles per second. So we have our rotation per minute divided by 60, and then our number of poles divided by 2, because for each, to get the full waveform of a sine wave, you need a north and a south pole. So we have a pole pair, north and south. So a 4-pole machine will have 2 norths and 2 souths. So in our example below, a 4-pole machine will give 50 hertz power at 1500 RPM and 60 hertz at 1800 RPM. So again, we're going to have that ratio of 60 over 50 times more power with 1800 RPM. So if the speed is cut in half from 1800 RPM to 900 RPM, then we'll have to double our pole count to achieve the same frequency. So we'll have to go from 4 poles to 8 poles. This can have an effect on the size of the generator to fit more poles in there. Our temperature rise is measured with either resistance of the windings or embedded detectors known as RTDs or sometimes thermocouples. This is often specified in 2 different ways, either as a temperature rise over an ambient, so for example an 80-degree rise over a 40-degree ambient, where the total temperature can exceed 120, Class B per NEMA, or it will be given as that class rise per a given ambient, so it will be specified as a Class B rise in a 40-degree ambient. So here we have table 32-3 out of NEMA MG1, and this is for air-cooled machines. And this is based on a 40 degree C maximum ambient temperature. So you can see the different temperature rise levels or the insulation class systems. A is not commonly specified anymore. So a B rise, you'll typically have an 80 degree rise by resistance over 40 degree ambient. An F rise will have 105, and an H rise will have a 125 degree rise when measured by resistance. If we have a lower kVA or a lower voltage, we can have a 10 to 15 degree increase in the measurements with the embedded detector. This is because the embedded detector is measuring a hot spot, and it's right inside the slot, which is typically the hottest point. The resistance is measuring an average of the overall coil, so we're allowed a little bit more per NEMA in the hot spot than we are for the average. And our field winding, our rotor, we typically don't put RTDs in. I don't know if we can or if anybody does. It's hard to measure them when you have your field spinning. But those are, again, allowed to 80, 105, and 125 degrees. So generators may be rated as standby, and in that case, the previous table cannot be exceeded by more than 25 degrees Celsius. For an ambient temperature higher than 40 degrees C, the temperature rise in order to maintain that same overall temperature will have to be reduced by the same amount that you exceed. So if, say for example, instead of rating a machine at a 40-80, if we wanted it to be in a 50 degree ambient, we would have to rate it at 50-70 to maintain that 120 degrees overall temperature. TWAC machines The temperature is, the air cooling temperature cannot exceed the 40 degrees C for the air leaving the coolers without being derated. And this is one of the reasons that we can keep a TWAC machine in a smaller size when we have colder water, because it's being rated to be put in a room that's at 40 degrees Celsius, but the water going in that's actually cooling it is much colder. So here's another table to show those temperature rise classes. So for a 40 degrees C ambient, we can have between 0 to 10 degrees C for B and F, and 0 to 15 degrees C and H, depending on our kVA output and our voltage. The temperature rise for each is 80 degrees, 105 degrees, and 125 degrees. So the total overall temperature to be exceeded, or not to be exceeded, would be 120 degrees, 145 degrees, and 165 degrees. So the temperature rise allowance that we have directly impacts the size of the machine. And a lower temperature rise is going to require a higher machine, or a larger machine for a given kVA. So the temperature rise that we have, or the overall temperature that a generator operates at, is going to have a significant impact on the life of the insulation of the coils. And for every 10 degrees warmer that we run, the lifespan of the unit will be cut in half, which also means that if we run a unit 10 degrees colder, the lifespan will be doubled. So as we can see, for a Class B at 120 degrees, we would expect that machine to run about 30,000 hours. Well, if we look at the Class H rise, and we extrapolate that back all the way to 120 degrees, if we run that machine that's rated at Class H, but only run it at 120 degrees, we'll get much more life out of that generator, and we won't be worried about being limited by the thermal aging on the coils. So, Eliza, we have our next survey.
Thank you, Jacob. Yes, so it is time for our second polling question of the day. And the second question is, how would you rate your level of experience in specifying generator requirements? And the options we have today is bench warmer, no experience, rookie, minimal experience, pro, high level of experience, and MVP, expert. So if everybody would like to take a moment to make their selection, and I'm just going to remind you that if you do have any questions, just in order to ask them, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. And we will be addressing all of your questions in the Q&A. Okay, so it looks like everybody's made their vote. Let's have a look. Oh, okay, so we've got some mixed answers there. Very interesting. What do you think of that, Jacob?
Yeah, that's about what I expected. I expected more with a minimal experience than a high level or an expert.
Very interesting. Okay, I'll leave it to you now. Thank you.
All right. Thank you, Eliza. So we will continue on with electrical considerations. We have non-ideal loading conditions, such as motor drives, pulse width modulated devices, switching power supplies, fluorescent lamps, battery chargers, SCR controlled devices, unbalanced loading, it's important to know the highest level of unbalanced loading so we can size the machine accordingly. So we have curves are available for reference to estimate the machine size necessary for a given unbalance and typical curves. And the exact machine impact will vary unit to unit. So the more we know ahead of time, the more we can help with that. So our harmonic sources are typically caused by arc furnaces, transformers, fluorescent lamps, rotating machines, SCRs, pulse width modulated devices, switch mode power supplies, battery chargers, and adjustable speed drives. To meet the temperature rise, we'll have to be capable of handling the linear load, but also the nonlinear load. So we'll have to be able to handle that harmonic current with our generator. Also, to meet voltage distortion requirements, the harmonic voltage levels and frequency levels will have to be taken into account. Another thing to note is that the generator does produce some harmonic voltage itself, but a lot of the harmonic voltages are coming off of the power system that you're connecting. So here we have a typical D-rate chart for harmonic current, and per IEEE, our units are designed to handle up to a 10% harmonic current with no D-rate. So you can see at 10% we're at 100% of the generator rating. As the harmonic current increases, we have to dial back that generator rating, or to keep the same rating, we would have to increase the size of the machine. So for continuous unbalanced loading, we have the same thing, and we can see that across the bottom we have the maximum current rated, and we have the minimum current rated for a separate load. So if we have 100% of rated current on one phase, and then we can handle down to, looks like about 75% or 79% on another phase, and that changes depending on the load. So if you have that unbalanced, we may need to oversize the generator accordingly. So pole and winding pitch. And the pole pitch is the mechanical angle that the coil spans in the stator relative to the span of the two poles in the rotor. So as you can see in the example here, we have the two green dots simulating the two sides of one coil going into our stator, and they span 60 degrees of the 90-degree span that we have for a 4-pole machine, and 60 degrees divided by 90 degrees is 2/3. Key factors for this are the number of poles that we have, the number of slots spanned by the coil. A full pitch means that the coil spans the full length of the two poles, so in this case would be 90 degrees. Short pitched is anything less than that, and as we decrease that pitch, we impact certain harmonics, but we also decrease the output voltage. So why does this affect the sizing? Well, because it's going to decrease our output voltage, so we may need to change turns, we may need to add stack length, some other things to keep the pitch that you require and still be able to have that same voltage and that same output. Transient performance requirements such as motor starting or block loading. So each involves applying steps of the load at one time. Loads can be near rated power factor, or they can be a very, very low power factor, such as motor loads that can increase the amount of dip for that kVA. This is going to have an effect on sizing. So the voltage dip is driven by the machine's transient reactance. And so the dip percentage is going to be 100% times that x prime of d over the x prime of d plus the base kVA over the starting kVA. In the case of a purely resistive load, that base kVA and starting kVA simplifies out to 1. When we have a motor, that motor is going to have a much higher starting kVA because it acts similar to a short when you initially start it until your magnetic fields build up. So changing the reactances is going to affect the size of the machine, and particularly high reactances or particularly low reactances can both cause an increase in the size of the machine. So here we have an example of that dip calculation. If we have a machine that's rated at 2000 kW at 0.8 power factor with an x prime of d of 18.2%, and we want to start a 750 horsepower motor that is a code F motor, which means we'll have 5.6 starting kVA per horsepower, then what is the approximate voltage dip? Well, to fill in the variables in the equation, the base kVA is our 2000 kW divided by 0.8 power factor, so 2500 kVA. And our starting kVA is going to be that 750 horsepower times that 5.6 starting kVA per horsepower, which is 4200. We plug those into our equation and we see that our generator will estimate a dip 23.4% when that motor is started. So to help reduce that dip, we can either oversaturate the machine or make the machine larger. Oversaturating it is going to bring that x prime of d down, but that's also going to increase our rotor current and possibly cause the need to oversize the machine. So here we have a typical curve for the generator sizing dependent on the voltage dip required. And I would say that this curve is very conservative, and we can often do a little bit better than that depending on the size of the machine. This would maybe be a worst case scenario. But as you can see, the smaller voltage dip that you require, the higher the sizing of the machine goes. So we've talked about our mechanical enclosure requirements and our environmental requirements. Now we've talked about our electrical output requirements. So now we'll move on to the specifications. Certifying agencies that we often deal with are ABS, DNVGL, BV, LRS, RS, API, CSA, and UL. And then we also get certain requirements from the customer, either being the motor manufacturer or the end user. So our marine agencies, ABS, DNVGL, BV, LRS, and RS, will often have a minimum IP rating requirement. They will have limits on their temperature rise, and they'll also have transient performance requirements, typically less than a 15% dip at 60% load. API will have a maximum temperature rise requirement of 120 degrees, regardless of the ambient temperature. So if we have an ambient of 50 degrees, we'll need a 70-degree rise, so we'll need a larger unit for that. And they also have requirements for materials used in the generator, which will increase the cost with the specialty materials. So customer specs can contain just about any of these items discussed so far. They can be simple for a machine and require no special machine sizing. If they become complex, the machine can be 2 to 3 times the size of an equivalent ODP machine. So performance of the machine can be specified in a variety of ways, and the details are very important. Don't filter any specifications. We prefer to get all the specifications up front, even if it's too much information sometimes. Something that catches our eye might not necessarily catch your eye as something that we need to take into account when sizing the generator. Clear communication is critical up front to make sure that we get you the correct machine that you need. If there's any doubt, get clarification from the customer as well as the supplier to keep everyone on the same page. And if you're interested in learning more about generator design and not just sizing, we do have our Gen Schools annually. Our 2019 date has yet to be decided, but we'll talk about the electrical and the mechanical design, the sizing and testing, the controls, some standard features and options, some maintenance and troubleshooting schedules. This is open to our customers and end users. And if you're interested, you can send an email to genschool@mail.nedec.com, and we'll make sure to get you more information when we know when the 2019 Gen School will be. So there are many details that go into the sizing of the machine. It should be left up to qualified professionals. I know that I threw a lot of charts and graphs at you here today, but every machine, every frame size is a little bit different, so it really takes an in-depth analysis on each unit. The more that we know, the more that we can help you out, so include every detail. If you're unsure about whether a detail will affect the generator, send it to us. We'd rather have too much information than too little. So if you have any additional questions, you can always contact us at catoengineering@mail.nedec.com. So, Eliza, that's our last slide. If you would like to kick it off with questioning. I do also have Winhorn here with me to help fielding any questions. He's a senior electrical engineer here. He has a bit more experience than I do on some things like control systems and grid code applications. So he'll be helping me field some questions.
That's great. Thank you, Jacob. Okay, so we've got a lot of questions here. So I'm going to kick things off. The first question today is, how much buffer do you recommend on top of total calculated load when sizing generators?
Can you say that again?
Yes, sorry. How much buffer do you recommend on top of total calculated load when sizing generator?
Ooh.
Yeah, I would say whatever your codes require. For instance, NFPA 110 and other codes have a requirement for the sizing of the generator compared with the maximum continuous load. But apart from that, none, because we size our generators to deliver the full load continuously 24/7. The only possible exception would be for if you want for extra life, you may want to size a machine for a Class B or Class F rise, even though our insulation is universally Class H, just to get a little additional life.
Thank you, that's great. Okay, and the second question we have today is, using the DG to supply mainly pump sand motors with VFD, what is the rule of thumb to determine the generator size?
So VFDs can be a little bit tricky. I think he's talking about the voltage dip required by it, or possibly the harmonic load from it. The voltage dip from a VFD-driven motor is typically very low because it's soft-started and brought up to speed, so the generator typically doesn't see much in the way of voltage dip. As far as harmonic loading, that's going to depend a lot on what type of VFD you're using. Could be up to 10% D-rate, perhaps.
Okay, that's great. Thank you. Okay, the next question today is, how much do you D-rate for 30% harmonic from VFD?
Same answer.
Be about a 10% D-rate on the generator.
Okay. The next question we have is the rise a delta increase, or is that the ultimate highest temperature, i.e. H class 125 equals 165 C ultimate temperature?
So that's correct. Yeah, Class H would be 125 degree rise over a 40 degree ambient. So the total temperature of the generator can see 165 degrees. So in the same way, if we put that same generator in a 50 degree environment, now we can only have 115 degrees of rise to maintain that 165 overall temperature.
Perfect, thank you. Okay, the next question we have is, what physical changes are made to the generator depending on the power factor selection?
So, particularly if we wanted a machine rated at a lower power factor, we may have to oversize the machine to give it a larger rotor to handle those higher rotor currents at that lower power factor. As far as being able to handle more of a capacitive load, we'll need to oversaturate the machine. So that, and oversaturating can draw a larger size machine, but also a larger machine will be able to handle more capacitive load without having to be derated.
Thank you so much. Okay, the next question we have is SKVA the same as KVAR?
No, they're quite different. SKVA is the starting KVA on a motor, and KVAR is the reactive load put on a generator from an inductive source or a capacitive source.
Okay, thank you. That's great. Okay, the next question we have is, what are typical allowable overloads for generators?
So we actually, in the widgets, we have our size, or our standards for overload, overspeed, overcurrent. Right. So our typical overload is 10%.
10% for an hour?
10% for an hour.
I think it's 25% for 2 minutes.
Yep, 25%.
And 150% for 30 seconds is the normal requirement of the standards, and we do meet those.
Okay, that's great. Thank you. Okay, I think we've got time for a couple more questions. So the next question is, how is ambient temperature determined for a TEWAC enclosure?
So the ambient temperature for a TWAC is the external air that the generator is sitting in. So if the room that the generator is sitting in is at 40 degrees C, that would be the ambient temperature. However, if we have colder water, say we have a 20 degree Celsius water flowing into the generator, the air circulating inside is going to be a little bit higher than that water. So say if that's 35 degrees, now we could have an 85 degree rise instead of an 80 degree rise for the generator compared to the air inside, because we're really cooling it with that colder air coming off of the water. But the ambient temperature is that outside air.
That's great, thank you. Okay, and the last question we have today is, what controls the power factor? Is it affected by the generator?
Well, I guess you could say it's slightly affected by the generator, because the generator does have a little bit of an inductive component to it, but it's very, very small compared to the load that you're connecting to. So for the most part, it's purely driven by the load that you have connected, how much of that load is inductive or capacitive, and how much of that load is resistive.
The only exception to that is if your generator is connected to a bus or some other source of power. In other words, if it's paralleled with other machines or with the grid. In that case, the generator excitation controls the power factor directly. But as long as the load is passive, there's no effect. The generator has no effect on it.
That's great. Thank you so much. Okay, unfortunately, that is all we're going to have time for today regarding audience questions. So that just leaves me to thank Jacob for what was a great presentation, and to Nidec Cato Engineering and Leroy Soma for sponsoring this session. To the attendees, you'll receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on our website and follow us on Twitter @BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again. I hope you all have a lovely day.
Thank you, Eliza.
Thank you, Jacob.